So let's start our discussion of Chapter 2 in Griffiths. And so we're going to look at the time-dependent Schrodinger equation. So again, here's this picture we have of the time-dependent Schrodinger equation right here. Now this is a partial differential equation. You may not have ever seen one of these before, and so we're going to go through and show you how one tool physicists like to do to solve these kind of equations. But again, just to reiterate, that the Schrodinger equation plays the role of Newton's second law. All right, and so we'll find that when we're done, what we'll be able to do is, given some initial conditions, basically the initial wave function, we'll be able to go through and find the wave function at all time, to sort of tell us how this thing will time evolve. And we'll see a lot of connections to, again, our rules of quantum mechanics from the Moore textbook. So here is the equation. Now just one thing, for right now, we're going to assume that the potential here, this is the potential, like you may have used in first year, is independent of time. So it only can depend on the position. And this is our potential energy function. And what we're going to do is we're going to assume a separable solution. And what does that mean? Well, that means that our solution, psi x of t, consists of two functions. One function that depends on position and one function that depends on time. Now we're going to find that this limits us a lot. Okay, this won't include every solution, but by doing this, we'll be able to use these solutions in a very powerful way to do most of what we need to do. Okay, but the key is there's two functions, and so we sort of call this lowercase psi of x. So we've got to be careful. It's unfortunate that it's the same sort of shape as this, but this is sort of uppercase psi, this is lowercase psi, and then phi of t. And so then what Griffiths does is he goes through, and so let's calculate these derivatives. So we want to calculate both of these derivatives now. And by making it separable, basically one of the functions is essentially constant. So here, when I take the derivative of the wave function with respect to t, okay, and this is a partial derivative because I'm taking it of both a function of both x and t. However, it only affects the function of t. It doesn't affect the function of x. So it treats the function of x as a constant. And so one thing is, just to make this easier, the textbook and I will suppress these function of things. Just realize that the lowercase psi is a function of x and the lowercase phi is a function of t. But so what happens here is basically the psi is treated like a constant, and so when I take the derivative of this with respect to time, I get the constant of that and then times d phi dt. And a very similar thing, so this is taking two derivatives, but it's the same sort of idea. We treat the function of time as essentially, it's a constant, and so we end up with just two derivatives of the psi function with respect to x. Okay, and then what we do is we take these and we just literally plug them back in. So I plug this back up into here, and I plugged this back up into here. Okay, and so when I take that over, what I have is something looking kind of like this here. Again, I plugged in this term for the derivative with respect to time, and then this term for the double derivative with respect to x. And then what we're going to do is we're going to do this thing where we're going to basically take both sides of our equation. And you can think about it different ways, but how I'm going to think about it is I'm just going to multiply by 1 over my wave function, which is that curly psi times the phi. Okay, so I'm going to multiply by 1 over the curly psi times the phi. And so when I do that here, what happens is this curly psi and that curly psi cancel out. And then over here, so these two guys will cancel out both of these. So we again, I should have mentioned that here for the wave function, I just multiplied by how we had our definition, which was the psi times the phi. And so when I multiply this out, it'll distribute in, and so it'll be the psi times the phi here. So those two pieces will cancel. And then over here, it'll be the psi times the phi, and the two psi's will cancel. And so when it's all said and done, we'll notice that over here, so I have this 1 over phi left over. These are just constants, and then this derivative here. And then over here, again, the phi part canceled, and so here I have 1 over psi times all of this stuff. And then here, because that wave function is essentially canceled out, I have only the potential left over. And we notice something that's really important. Okay, we notice that one side of the function is a function of time. So this side of the function is, or this side of our equation, only depends on time. It's constants and then functions that depend on time. And this side over here is constants and then things that depend on position. All right, and whenever we do this, okay, what we can say, and so I can sort of think about it this way. So basically I have an equation here where, like, on one side it's some function f of t, and that equals some function g of x. And this will happen to you sometimes, and it's actually a good thing, because what that means is both of these sides of the function have to equal some constant. All right, and if you just think about this, you might have to think about this for a little bit, but basically what this means is, imagine if I held x, at constant and then changed time. In order for this equation to still be equal, the only way that can happen is if these functions equal a constant. All right, so think about that for a little bit, but that's the way it works. And now, because Griffiths knows what this constant will end up being, he makes a really inspired choice to call it E. Okay, we'll find that this will eventually end up being the energy. And so then what we've done is we've taken this partial differential equation that was very scary looking, and we've broken it down into two differential equations that are, probably still scary, but they are much simpler. And so now we're going to go through and solve these two differential equations individually. All right, we've done a lot here, so I definitely suggest going back through this if you need to, just to make sure you're on board, because this is something probably different than what you've done before. And so now we're going to go through and look at these two equations. I'm going to start with this one right here. Now, this is not a course on differential equations, so we'll talk in class. There'll be a few differential equations that we'd like you to be able to recognize, but this one is not one of them. But basically a differential equation, so it's something that involves a derivative, all right, and generally some functions of a particular variable. And so here, this is a differential equation. What I can do is I can take this and basically write it this way here. Okay, and so it's got this derivative equals this. And when you can do this, what I like to think about it as is we're trying to search for some function phi, okay, and this is a rule that phi has to satisfy. And what that rule says is that if I take the first derivative of phi with respect to time, it equals some negative constant, like this thing here, times the function itself. And so our goal for a differential equation is to try to find what function does this. Now again, we're not going to spend time solving them for this case here. You'll take a class in this at some point and you'll get better at this. But for now, we want to be able to recognize that this does solve that particular differential equation. And so, for instance, I can take it back over to here and actually let's take the derivative of this with respect to time. Well, this is an exponential, and so if I take the derivative, I'll end up with the function itself, all right, times the time derivative of these upstairs pieces. And so I get negative I e over h bar. All right, and we see that is exactly equal to negative I e constant h bar. And of course, this is our function itself, phi. And so, in fact, if I do take the first derivative, I get back this constant times my function itself. And so that's what this differential equation says. Now, more importantly to us, what we've seen now is how the time evolution works for this particular wave function that we've set up here. All right, and we're going to see that this is justification of the rule 7 from Moore. Okay, and so this basically comes out from the Schrodinger equation. If you remember, if you go back to rule 7 from Moore, you'll recognize this piece here. Okay, so we're going to talk much more about this, but at least you can kind of see where this comes from in our equation here. And so now we have these two pieces. So the time equation we basically solved. We got this function. We're done with that differential equation. We're not done sort of trying to understand what this means, but we're done with that differential equation. And so we're left with the other differential equation. So remember, we took our time dependent Schrodinger equation. So we started with what I call the TDSE, and we split it into two equations. One of them gave us this, and the other one is this over here. And this is going to be called the time independent Schrodinger equation. And we're going to spend basically the rest of chapter 2 solving this for different potential energies. So we'll have different systems with different potential energies, and we'll go through and solve this equation and try to understand it a little bit better. Now, one thing, if you're like me, all right, you had never heard the term Hamiltonian before, and so I just wanted to kind of talk about that. In classical mechanics, there are basically many different ways to get the right answer that are essentially equivalent, all right? And one of them that we know very well is Newton, right? So F equals ma is one way. We can take F equals ma and solve for the position of time for something, and we've done that with, say, like projectiles or something. There's other ways that people, as sort of physics progressed, that they figured out were just equivalent ways of doing it that can sometimes be insightful. And I looked up, there's basically like more than 10 of these things. Lagrangians are a thing you might be doing in your 254 class. Now, two that you generally don't see until maybe third or fourth year mechanics would be the principle of least action and what's called Hamiltonian mechanics. All right, and so the Hamiltonian is a different way, an equivalent way that you can go through and, again, get the same stuff you'd get from Newton's law. So it's not like it's anything new, just a different way to formalize it. And so the Hamiltonian is defined right here for us, again, just as the kinetic energy plus the potential. Okay, so it's just the kinetic energy plus our potential energy. So you might have used like PE for this before, but now we're using V. And again, our kinetic energy is just P squared over 2m, just the classical kinetic energy. For this point, I think you can think about it as more of just a definition. Okay, I'm not sure, I don't think really understanding the full machinery of the Hamiltonian mechanics from third year is going to help here. But it's just, this is what people call this. And so I think it's something new and kind of different. Now, at some point, we're going to make a transition. Griffiths will do it. And basically, so we've been calling this thing here psi. And so now we're going to define it. We're going to find that for each system, so it's a little bit hard because we haven't actually done any systems yet, but for each system, we're going to be able to solve for a bunch of psi's, and we're going to number them. There'll be an infinite set, so psi 1, 2, 3, 4, 5, etc. And so for the general equation, we'll just call it psi of n. And what's going to turn out, we're going to see in the next couple of slides, is that each one of these psi's is an energy eigenfunction, okay? And so these are similar to energy eigenvectors that we talked about in the Moore text. Okay, and so this will be a particular function that if my particle is represented by that function, then my particle has a definite energy, and we'll see that in a little bit. Okay, and just to get a little bit of sort of discuss a little bit about this is there'll be times when we'll look at this. So this equation again is the TISE, the time-independent Schrodinger equation. Here's a differential equation. We'll look at it as a differential equation very often, but you can also look at it as an eigenvalue equation. So we talked about eigenvalue equations last week, and basically the way that works is there's some operators. This is the Hamiltonian operator, and we're going to find that the Hamiltonian operator, its eigenfunctions are eigenfunctions of definite energy, and so that's what this equation here means. So these functions, so basically there are psi n's that when I attack h on the psi n, I get en times psi n, and then en, of course, is our eigenvalue. That's the actual value of energy. So if I'm in the psi 1 state, I know that my energy is E1. And just real quick, the operator here is just basically negative h bar squared over 2m d squared over dx squared plus Vx. So this will be a handy way to look at this in some cases, all right? And hopefully this idea of energy eigenfunctions, okay, we're going to use this a lot. Okay, so I just want to stop and just be real clear with this. So these are really important things to us. We're going to spend most of the rest of the semester trying to understand the full implications of this, okay? And so, but the first thing that's kind of confusing is that these solutions that we just saw for have a couple different names. So right now, Griffiths is calling these the separable solutions, and that's just because these are the solutions where, you know, we sort of assumed that our solutions could be a function of x and then some function of time. All right, so we separated the two variables, and so that's what we mean by separable solutions. So these are super important. Now, two things we're going to find out just next is that if you're in one of these states, so this wave function can represent the state of our quanton. If you're in this, nothing's going to change. All right, and so if you're in one of these particular separable solutions, okay, we call it sometimes a stationary state because nothing changes. You'll see that everything, expectation values and stuff will remain the same. Another thing that we just talked about, all right, is that we're going to find that these states have a definite energy. And so we're going to call these states also the energy eigenfunctions. So basically these things are so important, there's sort of three things we call them. Now the separable solutions was just sort of the math thing, so we won't bring that up very often. I will pretty much call them this here, but just be careful because sometimes the textbook might refer to them differently. And so to me, I think of these things as the energy eigenfunctions. Is that we'll move forward thinking about them like that. Okay, just to kind of sort of flesh some of this out. So again, here's our separable solutions. Now if I take over here, if I go ahead and take the absolute square of the wave function, okay, and you can do this, we've seen this before, the time part will cancel out. And so it only depends on position. And so if you go through and calculate any expectation value for this particular wave function, okay, they'll all be constant in time. And so again, if the state of your system is represented by this particular wave function, nothing will change with time. We call it a stationary state. Okay, we'll also see that these are states of definite total energy. We call those energy eigenfunctions. Now the way to do this is to find the expectation value of our Hamiltonian operator. Now the Hamiltonian operator is our energy operator. And so the way we do that is we sandwich it in between these two things here. Now just remember, we just talked about how you can think about this as a eigenvalue equation. And so sometimes it's really convenient to think about it like this here. Okay, and so what happens is when I apply this onto my psi n, there should be an E sub n right here, I get this energy eigenvalue E sub n. So this turns out to be E sub n here. Now this is just a constant, so I can pull it outside of my integral, and then the integral that's left over is just our normalization condition. So we assume that these are normalized. That equals to 1, and so the expectation value of the energy is E sub n. Now we'll do this in class, but you can actually go through now and check it yourself. But if you calculate the expectation value of h squared and then take the subtraction of the 2, which gives us our sigma, you get 0. So sigma of 0 tells us there's 0 spread in this thing here. And so the energy for this state is E sub n, and it's always E sub n. So just to quickly summarize, these solutions are stationary states. If you're in them, nothing changes. They're also states of definite total energy. And finally, another really important fact is that the general solution, okay, the general solution to our time-dependent Schrodinger equation will work out to be a linear combination of these separable solutions. So we mentioned when we first went down this separable solution path that, you know, this won't include every solution, all right? But what it turns out is that because you can write any solution as a linear combination of these solutions, this will be a way to basically help us solve every kind of problem we need to. Okay, and so any solution to this equation I can write as some linear combination. So here's a little Cn, which we'll see will be very similar to the Cn's we've dealt with before. And so just to kind of talk about this a little bit, again, we want to draw analogies from this new wave function stuff. Okay, back in our rules of quantum mechanics, we could express the spin state of any quanton as a linear combination of the plus z and the negative z spin eigenvectors. Well, the same thing now. I can express any wave function I want as a linear combination of the energy eigenvectors. All right, and so this, you know, is a direct sort of analogy. So here it was these spin eigenvectors, and you got to be real careful over here. These are eigenfunctions. All right, and so we're going to find a direct analogy here. In fact, if you remember, A and B, right, helped us to get information about probabilities. The absolute value of A squared was the probability I'd be measured in this state here. Well, if I take the absolute of this value of this C1 squared, it'll be the probability that I'll be measured to be in this state, which is meaning that the probability that I'll have energy E sub 1. And so we'll see a lot of direct connections here. And then finally, just to kind of get a little bit, sort of tell you where we're going. So this is our general procedure for solving any kind of problem. Okay, so in Chapter 2, we're going to basically solve the time-independent Schrodinger equation for different potential functions. And each time what we're going to do is we're going to find the particular eigenfunctions, the particular energy eigenfunctions for that potential energy. all right? And then what we'll do is we'll be given some initial wave function. And so what we'll do is we'll learn tricks to represent any wave function as a linear combination of these energy eigenvectors. And then to time evolve it, just like in the rules of quantum mechanics, we'll multiply each energy eigenfunction by this term here, which we should recognize from the rule 7 from our rules of quantum mechanics. So we'll talk much more about that.